So we have experienced a list of activation functions. Now let's see how we can utilize this ANN for simple problems. We will start with a very well-known problem we have already experienced in our previous lectures. The it is nothing but linear regression again. Okay. So now I have concept of artificial neural network in my hand. Using this, how I can solve the problem of linear regression. So, as for example, a very simple task is given that forecast the monthly sales by studying the relationship between monthly e-commerce sales and online advertising cost. Naturally, the advertising cost will be the input and output will be the monthly sale, right? And you already have idea what exactly looks like for a linear regression curve. It looks something like this, where this particular, the equation of this curve I have to find out. What is this equation in general? We say y equal to mx plus c. But if I want to represent in form of artificial neural network, then we can write in form of like this. You see, so y1 equal to sigmoid of w11x plus w12, where this w11 is representing basically the slope and w12 representing the intercept. Now if I want to represent a simple neural network model for this, I can do a diagram, draw a diagram like this, right? We have some summary here. There are two neurons. One neuron have input x. I'm sorry, there are actually one neuron only in the input, that is x. And this is what you can say bias. What we do, we always keep value of bias as +1 conventionally. Now you will say, if it is always 1, then how it will impact differently in different problem? It will impact differently in different problem because this bias is not directly connected with this summary. It is connected via a particular weight value, that is W12 presented here. So if this bias does not have much requirement to solve the issue over here, then naturally you will see the value of W12 will become very low. And if this bias demands a lot of importance for designing the model, then naturally you will see the value of this weight, which is connecting the bias with this summer, will be very high. So these WRs are the adjusting parameter. That's why these are called free parameters. And your input will be through this particular neuron only, because we have only one input, the advertising cost. That is the input. So only one neuron. That's why you have only one output. That is a monthly e-commerce sale. That's why you have only one output in this side. And the other things remain same as you have seen in Macular-Pitts model. Like you have a summer, that summer will basically, summing up the W12 into +1 plus W11 into x, like this. And we will have some activation function here. That activation function can be a sigmoid function, can be signum function, can be tan hyperbolic function, can be any function. And based on that, we will get some output. Now, definitely, sometimes it is also a part of research that which particular activation function will act best for fitting your data in that particular model. You cannot always say that for some particular specific type of problem, always say sigmoid function is the best. You cannot claim like this. Okay, so it's also a part of investigation. So you can try with various activation function and check which particular activation function works best for your model. Okay. Anyway, let's continue with this. Anyway, since we are talking about linear regression, another old concept will again come in front of you. Can you guess what it is? Basically nothing but gradient descent algorithm that already you have experienced, but in a different way. Now we will do the same thing for a artificial neural network. Okay, so let's see. So assume that we have a artificial neural network like this. You see, it's a bit complex now. Bit complex in the sense we have two outputs here, not one output. It is possible. There is no guarantee that always your neural network will have only one output, because maybe you want to predict more than one things. In that case, what will happen? You need two outputs in that case. And obviously the number of feature will vary from 1 to n can be anything, right? So accordingly the number of input neurons will come. And interestingly, you see that all these input neurons are directly connected with all the output neurons, because we believe that the outputs are somewhat influenced by all these input neurons. Maybe some neurons have less impact, some neurons have very high impact, but somewhat they are connected. Now, by the nature of the data, if it demands that for a particular neuron should be very less inactive, automatically the weights will be adjusted accordingly. That already I have mentioned. So you see, for each and every independent connection, we have independent weight values. And you see how I have named the weight. This is x1 and this is y1. That's why I written w11. This is x1, this is y2. That's why I've written w12. Similarly, this is x2 and this is, here it is connection y1. So connection between x2 and y1 as w21. So here wij represents ith neuron to jth neuron. As simple as that. Okay. So I am assuming that this y1 is one of the outputs and y2 is another outputs. Okay. So naturally, we will have, I'm predicting output from these output neurons, and I have an actual output in my hand, because we are talking about supervised learning. If we have, naturally we can easily calculate the error, because calculating error is the first step in gradient descent algorithm. Already you have seen in the previous video. So we will, as usual, we will start with the same calculation, that error is 1 by 2 summation over j 1 to 2 tj minus yj. Why 1 to 2 given? Because there are two neurons, two outputs. So that's why 1 to 2. I'm just reflecting this equation based on the data over here. Okay. Anyway, so basically what we have to find out, again we have to find out the gradient of the error with respect to the weight values. Because if you recall, in gradient descent previously what we have done, we have done gradient of error with respect to c and with respect to m. What are those m and c? Those are the free parameters of any straight line by which you can adjust the the straight line direction. Not direction you say, but I will say the straight line nature. Similarly, here also we are trying to find out the equation of the straight line in with the use of artificial neural network. So here that m and c is represented by some weight W. That is the only difference. So that means we have to find out the gradient of error with respect to all these weights individually. We will find out. Once we find out the gradient of error, that gradient will be multiplied by the learning rate eta. If you can again recall that. Anyway, if you cannot recall, still we can proceed here, you will understand. So it will be a brush up for you for the gradient descent, but in a different way. I hope this will be very interesting. So let's proceed. So basically we have to find out the gradient of the error with respect to all these W. So Wij, that's I have written, because all these W individually. But it's not possible to do it directly, because you know how you will do this. This output, I mean this error E, actually a function of the output. Because of the output I have got this error. This error is a function of output Yj. Tj is my target, that is fixed always. But depends on the iteration, this Yj will vary. So this E is output of Yj. So you cannot directly find the gradient of error with respect to W. But what you can do, you can find the gradient of error with respect to this output Y. And separately, you see this Y output is some function of this W, because Y is basically nothing but some function of the summation value of this x1 w1, x2 w1 2, sorry, x2 w21, then x3 w31, like this. Just think about only y1 neuron. Forget about y2 neuron time being. So if we talk about only y1 neuron, it is connected with x1, x2, x3 with the help of w11, w21 and w31 weight. This x1, x2, x3 is also fixed. These are the inputs. What will vary? These w's will vary. So that means the output y is somewhat you can say a function of these w's. So just see. So we have a branch, chain calculation we can do. Derivative of error with respect to w we can calculate by derivative of error with respect to y multiplied by derivative of y with respect to w. And this, it is nothing but a chain differentiation, right? So once you will get this, you can say the expression of this derivative and expression of this derivative, you can easily calculate them. So let's do one by one. Let's see for derivative of error with respect to y, how it will look like. You see, from the equation 1, it's very easy. If you write derivative of error with respect to y, this 2 will come out here and the 2 and here by 2 will cancel each other. So that's why the half is given, just to create a easy solution for the derivation. If you don't put here half, then what will happen? Only multiplied by 2 will come, and it will simply it's not a, I'll not say it's error, it's wrong, but I will say it will create complex operation which is not required. So if I just do a chain differentiation, these 2 will come out, 2 by 2 will be cancel each other, and what I will get? I will get, it's like x square. So 2 will come out, then minus tj minus yj, minus of this definitely, tj minus yj, and then you see why minus is coming here. The reason is that this tj is fixed with respect to this error, with respect to the output. So derivative of error with respect to y, where this is tj, is 0, and derivative of yj with respect to y, it will be minus 1, because I have a minus sign here. So as a result, if you only do the derivative of tj minus yj by yj, derivative of tj minus yj by derivative of yj, then you will get minus 1 as a result. So that minus 1 is multiplied by tj minus yj. So it's simple derivative calculation. You can easily do this, in your copy in your home. So basically, you know, this yj. Now question is that what this exactly yj is. This yj is basically every, any y. Take y1. Take y1. This y1 is basically calculation, is a summation of the multiplication of x1 w. It's like this. You see wij into xi. I equal to 1 to 3. Why? Because there are 3 x's, 3 features, input features. That's why you 1 to 3. It's for a single y. I'm telling you. Right? Now, in this function, you can see this w is a free parameter. So, from this equation, I can calculate derivative of yj by w. So, if I do that, what will happen? It will be derivative of, d dwij will be like this. And since wij is at the in the denominator, so naturally this will get vanished. Right? This wij will cancel. It's like it's 1. ddx of x, it's 1. Similar thing, ddwj of wj, it's 1. Whatever, doesn't matter, x, I 1 to 3 or whatever. So only xi will left. That means the derivative of yj by derivative of w is equal to nothing but only xi. W means wij. It's only xi. So you have calculated, we have calculated the first term as well as the second term. Now what you have to do? We have to just do the multiplication and find the final expression of derivative of error with respect to wij. Right? So now we will get like this. If I just combine these two, I will get minus tj minus yj multiplied by xi. And that is what the derivative of wij is. And what this is nothing but the derivative of error, that is a gradient of a particular weight, considering j as the output unit and I is the input unit. Right? So we have established the formulation of the derivative. Right? Now how we can utilize this? It is nothing but the the delta, the correction that whatever we require, if you can recall again. So the direction of the correction of the error, as you know, the opposite to the direction of derivative, already I hope you can recall, like in previous video also is given here in the previous slide. It was the slope direction and we are going in this side. Wherever, maybe you start from this side or this side, you go in the opposite direction of the slope, That's why naturally the minus tij that I had, this minus will get cancelled out here. So minus eta into minus tj minus yj supposed to be the actual equation, but minus eta and minus tj minus yj, so this minus will cancel each other. That's why I have not written any minus here. I have written only eta multiplied by tj minus yj into xi. What is this eta? This is the learning rate. Already you have seen when we did the code of the linear regression from scratch. And this delta wij is nothing but the correction that we have. Delta wij is nothing but the learning rate multiplied by the gradient, I mean multiplied by the derivative. That is what I have done. So once you will get this particular delta wij, you can simply add this delta wij with the present value of wij to get the new wij, and this should be my end goal. I have kept here new old in a bracket just to show you that it's in ith. This wij old is in the ith, you can say ith iteration, and the new will be nothing but for the I plus 1th iteration, the next iteration next value of the next value of w at the next iteration that will be used. So these two equations is very known to you. You have already experienced this in a different way, but before that, the it's now what we have done it with respect to a flavor of artificial neural network. So now what we can do, we can start understanding different types of artificial neural network possible. Okay. So specifically, if I say the neural network or artificial neural network that we are using to understand the gradient descent and so on and so forth are called single layer perceptron. What is single layer perceptron? Let's see.